Hello, my dear students, and welcome to a new chapter with our analog electronic design aspects. In the previous chapter, we have a long story with different RF-based analog filters, considering single-stage, cascaded, and switching capacitors based filters, also SAPs or single biquadratic amplifiers. And also, finally, we terminated the chapter with an important RF tuned amplifiers. Now we are going to start a new chapter, and actually this will be our terminating chapter for this module under the titles of oscillators and wave shaping functions. So let me first start, as usual, with sharing the presentation slides of the chapter. So I believe now you can see my presentation slides here. Okay. Perfectly. So this is our chapter 3 with the title of signal generation and waveform shaping circuits, or what we can simply call it oscillators. So maybe the first point is, as usual, is to highlight that this chapter is found in our microelectronics reference by Sadra. As I mentioned in each and every chapter, this is based on the 6th edition or the 7th edition indexing. So it's chapter 18. However, this number may differ from one chapter or from one version to another, but still having the same title. Okay, so as I just mentioned, our main concern in this chapter is toward oscillators. So maybe the first question to be answered in this chapter is, what is oscillators? Or generally, what is the difference between an amplifier and an oscillator? Maybe in the first chapter, as well as in the last portion of the second chapter, we have somehow dealt with different type of amplifiers. And I think all of us know basically the definition of an amplifier, where you have an input signal and have an output signal. And this output signal should be an amplified version of the input figure. This amplification can be RF based, or what we can call a tuned amplification, as we already observed in chapter 2, maybe a cascaded amplification stages with an output stage power amplifier, as we say in chapter 1. But in all cases, we have an input and an output, and the output is an amplified version of the input. This is the main concept. In oscillators, life is relatively different. In oscillators, actually, we don't have inputs. We only have outputs. So a function of an oscillator, and I think all of you may already hear the word oscillator before, maybe in electronic courses as well as in communication courses as well, when you consider these modulators and sometimes demodulators, and you need an oscillator to generate the carrier frequency. So the word oscillator generally related to the term of generating a sinusoidal signal without having an input AC signal. So what do we mean here by input is an AC input. We don't have an AC input, we just have an AC output. So how we can generate a signal, how we can generate a circuit that can have an AC output without an AC input. This is mainly the concept of oscillators. So let's consider it in this way. Let's consider that our targeted circuit is a part of two subsystems. We have an amplifier, a normal amplifier, operational amplifier-based circuit that do some sort of amplification process. So this is, let me use a highlighter. So this is simply the amplifier, an amplification circuit. And on the other hand, we have what we can call an RLC network, which should perform, based on what we already have learned in the previous chapter, this should perform some sort of amplification, some sort of a filtering process. We already know that this RLC circuit should perform some sort of filtering process. So we have an amplifier and we have an RLC or a frequency selective network. We call it A and beta. So A stands for the amplification process, and beta stands for the the frequency selection process, or simply the transfer function of a filter. These two subsystems are connected in what we can call a positive feedback network. So the output of the beta selective frequency selection circuit is inputted to this circuit. But what's really interesting is we are going to get rid of these inputs. So that assumes that we don't have an input. So it's just a closed loop of getting the output of the frequency selection network to be positively fed to the positive terminal of the amplifier and so on. So that we can consider that the transfer function of this circuit or of this system will be in the form of A over 1 minus A beta. As you can see here, my dear students, we make a generic form of this transfer function, considering what's called A of S. We already know that S is J omega, so it's this amplifier can be a frequency-dependent amplifier, as we already studied. And definitely, beta should be a beta of S because it's already a frequency selection circuit. So by default, it's a beta of S. Okay, so let me go to my whiteboard for a while. Sorry, I think I need to shift this. Yes. Oh, perfect. So, as you can see, my dear students, we have here a transfer function called A of S over 1 minus A of S times beta of S. Okay. What if you manage to have this term, which is AS beta S, to be equal to 1? Okay, what will happen here that this denominator will tend to 1, will tend to 0, or in other words, your transfer function, in this case, will tend to infinity. If you remember, my dear students, this was the instability factor in the analog filter design. If you remember, when we managed to have bools and zeros for a filter, we mentioned that we have to force all the poles of a filter to be in the negative sigma axis so that we can ensure that these points will not physically occur in the system to avoid this infinity instability factor. Alternatively, here in this case, we are forcing our system to be unstable, or in other words, to be with an infinity transfer function. So, what is an infinity transfer function? Simply, a transfer function represents a relation between the V output and the input. So, in order to have an infinity transfer function, mathematically wise, you have two options. A first option is to have V output equal to infinity, while or with the condition that V input is not equal to 0. So in this case, you will have an infinity of a constant over constant, which is infinity. But you can easily understand that this is not a physical assumption because physically we don't have something called infinity. So you can never have an infinity output because physically there is no infinity. And the other way to get a transfer function equals to infinity is to have V input equals to 0, while V output is not equals to 0. Because if the output is equal to 0, that means it's 0 over 0, which is an undefined value. But whenever you have a constant over 0, the output is, or a finite element, a finite number over 0, the output is infinity. So this is typically what we are searching for, my dear students. We are searching for a circuit that can have some sort of a finite output with 0 input resistance. Sorry, zero input voltage. With a zero input voltage. So this can happen if we manage to have this AS times beta S equals to 1. In this case, you can enforce your transfer function to be equal to infinity, which lead to a case where you have an output voltage, a finite output voltage with a zero input voltage. So this is simply how we can understand the concept of an oscillator. So back to our presentation slides. Okay, perfect. So in this case, we have what we will call L of S, which is simply the multiplication of the transfer function of the amplifier, A of S, and the transfer function of the frequency selection circuit, beta of S. So we can consider it in the way that L of S should be equals to 1, or L of omega should be equals to 1. But here, if you just recognize, we don't say that it's L of J omega. We say that this is L of J omega node, because simply this is a frequency selective circuit. Please remember the last video related to resonance. So herein, you are not going to have this infinity transfer function everywhere in terms of frequency. No, it's only a selected frequency at which this condition occurs. So for only the selected frequency, an infinite transfer function will be generated, or you can make the concept of an oscillator. That's why we use the term L of J omega naught to specify that this L condition to be tends to 1 will occur only at a specific oscillating frequency omega naught. In other words, you can consider it in a very easy manner. So if you say that this is your beta selective network, and this, of course, represents the output signal. So basically, the signal generated or outputted from the beta selected network is equals to beta times X naught. So XF, which is the feedback signal, equals to beta times X naught. Alternatively, if you consider that this is X of F, you can say that the output signal here, which is X output, equals A times X naught. A times XF, sorry. So the XF is inputted here as far as the input is 0. So you have only XF. This XF is outputted here. So the output equals A times XF. By substituting these two equations together, you get the same conditions as A times beta should be equals to 1, and to have this oscillating condition. Okay. So let's start exploring some circuits to see how we can manage such an A beta condition to be equals to 1. Okay, so this is a first circuit. So starting from now, my dear students, once you see your oscillator circuit, you have to automatically divide this circuit into two subcircuits. Using this concept, we have an amplifier that amplifies some sort of an input signal. Then the output of this amplifier is inputted to a frequency selection network, and the output of the frequency selection network is connected to the positive terminal of the amplifier. That's why we have a positive feedback. So if we apply this approach to the given circuit, we can say that we have two input circuits now. Let me use that. So okay, the first one of this one, which is basically the amplifier circuit, this is a very considerable or a very standard non-inverting amplifier with the two resistance R1 and R2. And on the other hand, we have a beta selective network here, as you can see, my dear students, with an RLC filter. This is how we can divide our circuit. So In order to do the needed circuit analysis for this circuit, what you simply need to do is to calculate the transfer function of each of these two circuits. The one in the red square or the red box, which is the A of S, and the one in the purple box, which is beta of S. And then you can say that the multiplication of this AS and beta of S should be equals to 1 and search for the frequency at which this condition will occur. So let's do this. Let's start with the simple amplifier network here. So it's very straightforward. Here we have a negative terminal, here we have a positive terminal. The input is going to be inserted here, and here we have two resistance. This is R1 to ground, and R2 as a feedback signal to the output. Using our we have already investigated a lot of operational amplifier circuits before, so it's very straightforward. If this is the V input, then this will be V input, assuming an ideal operational amplifier. No current is going inside the amplifier here, so simply the current going in R1 is equal to the current going in R2. So we can write a nodal equation at this node saying that 0 minus V input over R1 equals to V input minus V output over R2. Accordingly, negative V input over R1 equal V input over R2 minus V output over R2. So we can get this V output here. So V output over R2 equal V input over 1 over R2 plus 1 over R1. Or what we already know, the final form for this relation is Y output equal V input times 1 plus R2 over R1. This is the final circuit here. So this is the final circuit. Okay. As you can see, it's not an A of S, it's a constant. But this is just a special case. So generally speaking, your amplification network may be a frequency-dependent network. Maybe we will see this in the next videos when we go to scale up to more complicated schematics. But generally, it might be an A of S, or it might be a frequency-dependent amplifier. But in this case, it's not a frequency-dependent amplifier. And this is actually well observed from day one, because we don't have any inductors or capacitors in this network. That's why we should have a pure resistive network here. So this is the first part of the equation. Let's now go to the second. If you remember my slide, the second purple box representing the other network, or the beta selection, frequency selection network. So our network, I just need to share the slide for a while just to show you something. So this is the slides. Okay, so as you can see, my dear students, now for the networking circuit, this terminal represents your input. So your input for this beta circuit is through this resistance, and your output is the terminal connecting the coil and the capacitor. So whenever I'm going to re-sketch it, I will sketch it in this manner. So I'm just hope that you didn't get confused. So this is the input R, and this is the L, and this is the C. Or in other words, we can say that this is SL, and this is 1 over SC. So basically, you can make the analysis. So it's very simple analysis. We have two branches in parallel. So we have SL parallel to 1 over SC, which will result in SL plus 1 over SC over SL times 1 over SC. Here S will be cancelled with us, so it will be SL plus 1 over SC over L over C, as you can see, my dear students. So this represents the term here. We can simplify it a bit by multiplying by S in the numerator and denominator. So S squared L plus 1 over C over L SL over C. Or you can make it maybe easier by still multiplying by C in both sides. So S squared LC plus 1 over SL. So this is represent the equivalent of this inductor and capacitor in parallel. So we have S squared LC plus 1 over SL. And in order to calculate this V output, so the V output is simply a voltage divider between this equivalent and the R. So you can write that V output equals the equivalent, which we just calculate, this one, we just calculated. So I'm just going to rewrite it here. So it will be S squared LC plus 1 over SL over S squared LC plus 1 over SL plus R. This is simply how it looks like. You can still multiply, or you can take here this SL as a denominator and multiply it here, so you can get S squared LC plus 1 over S squared LC plus 1 plus SLR. This will look like something like that, has a relation between the two. Okay, so I'm sorry, I think I did some sort of error of a mistake while doing the parallel equivalent, so I will repeat it quickly again. So we have here a resistance, a coil, and a capacitor. This is 1 over SC, SL, and R. So the most simple way is to calculate the admittance, or 1 over the impedance. So the admittance of this equivalent is Y equal SC plus 1 over SL. So the equivalent impedance of these parallel branches, this is my mistake in the previous section, which will be 1 over SC plus 1 over SL. Now you can make a potential divider between the equivalent of this impedance and the resistance. So you will get that V output equals 1 over 1 SC plus 1 over SL over 1 over SC plus 1 over SL plus R. Simply you can use this in the denominator to get 1 over 1 plus SCR plus R over SL. And then you can multiply these both sides, the numerator and denominator, by S to get S over S squared CR plus S plus R over L. And you can here divide both numerator and denominator by RC. Then you can get, yeah, now let's go now back to the presentation slide. So yeah, you will get, yeah, something like that. So this will be the function you will get by the end of the day. This is the beta function. So this is the R function, and this is the beta function. As we just mentioned, what we are targeting is to make R and beta, sorry, A and beta, the multiplication of A and beta tends to 1. So now we multiply A times beta. You can understand easily that your A is only an S-independent network. So you manage to have this A beta equals to 1. Then we can now remove S and write J omega. So you can write it in these terms of G omega. So you need this term to be equals to 1. You can see that this is not so difficult process simply because this 1 plus R1 over R2 is an amplification or a tuning parameter. So let's keep it away for a while. If you work to manage this term to be equals to 1, simply, if you cancel this term, I mean, if you put omega square to be equivalent to 1 over LC, this term will be canceled. And then you will have J omega RC over plus J omega RC in the numerator and J omega RC in the denominator, which ends to 1. So simply, a resonance will occur here when omega naught equal 1 over root LC, because simply when you have omega naught equal 1 to the root LC, this term will be cancelled. It will be negative 1 over LC plus 1 over LC, and then you will have this term. However, as you can see, it is impossible to make this term typically equals to 1 because you will still have 1 plus R1 over R2, or 2 over R1, which cannot be 1 because you cannot make R2 over R1 equals to 0. So what you can manage to do is that you can make this R2 over R1 slightly tends to 0 by making R2 much greater than R1, and then this term will tends to 1. However, this will not considered as a very accurate circuit for the first term, as I mentioned, because R2 over R1 will not typically tends to 0. In the other root, there is another important factor here related to what we call the saturation of your circuit, because this is a positive feedback circuit that is going to oscillate forever. So whenever you have any cycle, the output will be greater with respect to the previous cycle and so on. So this process will continue forever. So you will have a signal that is increasing forever. So you need to make some sort of a limitation or a saturation level to your circuit. So what we are going to discuss in the next part is how we can clip our oscillation to a certain voltage. So when I turn my oscillator and adjust it, for example, to generate a sinusoidal signal with 5 amplitude of 5 voltage, then I need the oscillator to oscillate till it reach 5. And so once it reach 5, it should clip to be 5 voltage. This is what we are going to see, or what we are going to discuss in the next part, inshallah. So thank you very much for this part. Let me see you, inshallah, in the next part with the limitation or the clipping process for an oscillation. Thank you very much.